Hi everyone, I'm John Boprosky and welcome to my webinar on how to create a perfect receiver analog front end with nonlinearity model from circuit data. Please type any questions into chat as I proceed with this webinar. I will have a questions and answers session at the end of the webinar. You can also email me with your comments and questions at johnb@serdesdesign.com. Why is this webinar needed? High-speed digital integrated circuit IC serializer, deserializer systems have their physical layer modeled and simulated in a channel simulator. Channel simulators are designed to use IBIS-AMI models that are based on IBIS specifications. Many commercial IBIS-AMI model generation tools cost tens of thousands of dollars to lease or to own. Today, the SerDes channel simulation technology has matured so that it is available for free using cloud-based tools at SerDesDesign.com. Included with the SerDesDesign.com tools are options to generate IBIS-AMI models from circuit data collected from SPICE circuit simulations. This webinar is to let you know about the process I have used for many years to create perfect models for a receiver analog front end with nonlinearity from circuit data. I created SerDesDesign.com to enable me to create and deliver IBIS-AMI models to 40+ high-speed digital integrated circuit companies over the past 10+ years. Over that time, I learned many processes that practically guarantee a better, more efficient, and automatic IBIS-AMI model building process using free tools. I learned how to create high-quality, low-cost IBIS-AMI models while avoiding the standard approach using high-cost tools. Along the way, I learned that expensive tools kill all chances you have of achieving low-cost, high-quality IBIS-AMI models. My tools are based on free tools: Microsoft Visual Studio, CMake, web browsers, HTML, JavaScript, and more. I learned that creating IBIS-AMI models should be the last thing you concern yourself with when it comes to creating IBIS-AMI models. Focus on collecting the correct SPICE circuit simulation data and use automation. My tools rely on automation to generate models from measured and simulated circuit data. I learned how to escape the costly commercial tool trap that keeps most persons stuck in a permanently high-cost model creation situation. Many of my tools are available for free on the web at SerDesDesign.com with options to download and install local copies on your Windows PC. I'm here to share my learnings over the past 10+ years and introduce you to the same IBIS-AMI model generation capability I have used to create and deliver high-quality, low-cost IBIS-AMI models. What this webinar will show you. This webinar first gives an overview of modeling SerDes systems in a channel simulator. Then I introduce the process I use to create perfect IBIS-AMI models for a receiver analog front end with nonlinearity. At small signal levels, perfect means that the IBIS-AMI model output waveform exactly agrees with the circuit output waveform. At large signal levels, perfect means that the IBIS-AMI model output agrees with the circuit output for peak and step levels, and with some variation in the pulse shape allowed as the signal goes into compression. Finally, I show you how you can get a copy of my receiver AFE with nonlinearity model generation tool for use on your Windows PC. Modeling a SerDes system in a channel simulator. Channel simulators are based on the IBIS Open Forum standard, currently at version 7.2. This figure shows a typical SerDes system block diagram to be simulated using a channel simulator. This block diagram is generic for any channel simulator, but each tool has its specific way to represent this block diagram. The constituent parts of this SerDes system include the following: the transmit IBIS-AMI portions. The AMI portion typically contains a transmit equalizer often in the form of a feed-forward equalizer. The IBIS portion provides a differential output to the channel. There's the transmit package, the channel, and the receive package. These pieces represent the differential channel. Each part is optional and may be represented using S-parameter files. There's the receive IBIS-AMI portions. The AMI portion typically contains a receiver continuous time linear equalizer, a clock and data recovery unit, and a decision feedback equalizer. The IBIS portion has a differential input from the channel. A key assumption to the channel simulator to keep in mind is that it considers that the entire analog content, the green area in this figure, the total channel between the transmit AMI portion and the receive AMI portion, is linear and time invariant. As an LTI system, the entire differential analog section in the SerDes system is accurately represented by its single-ended impulse response. The key concept enables this channel simulator to achieve its fast simulation speeds. Creating a perfect receiver AFE with nonlinearity model from circuit data. The IBIS-AMI model generation from behavioral data was built into the SerDesDesign.com channel simulator from the beginning. I have used this process over the past 10 plus years, providing custom IBIS-AMI models to over 40 plus companies based on the circuit data they provide me. In today's webinar, I provide instructions on modeling a receiver SerDes AFE with nonlinearity from circuit data. The modeling data is collected typically from a SPICE circuit simulator. This discussion is for a received SerDes with an AFE with nonlinearity, but with no CDR or DFE. Modeling with a CDR and or DFE is discussed in other SerDesDesign.com webinars. To start, let's talk about the typical SerDes system test points. This figure shows typical test points for a SerDes system. For the current discussion, test points TP0, TP4, and TP5 are used for data collection. A low-loss channel is assumed. NRZ data streaming is used for modeling. TP0 is the NRZ waveform. The data collected at TP4 is the input impedance of the input differential pins, the time domain waveforms at the input differential pair. The data collected at TP5 is the time domain waveform data at the AFE with nonlinearity output, the VN versus VOut characteristics capturing the nonlinearity, and drive levels are from small signal to saturation. The receive circuit input impedance is measured at TP4. The receive SerDes differential input impedance is measured with an input load resistance of 50 ohms per pin, 100 ohms total. The S2PS parameter data with touchtone 1.0 format is collected at TP4 from 0 Hz to Fmax in steps of F-step, where Fmax is greater than or equal to the 2 times the symbol rate, and F-step is less than or equal to 10 megahertz. This data is collected for each receiver's SerDes corner case. This data is used to create the receiver input IBIS buffer model as an S4P file based on the IBIS-AMI 7-point specification or later. The receiver modeling data is collected at TP4 and TP5. The modeling data is collected in the time domain. Even if the system is using PAM4, the modeling data is NRZ. The NRZ waveform data is used to create the IBIS-AMI model and for NRZ verification. If PAM4 is used by the receiver SerDes, then additional waveform data may be collected using PAM4. This PAM4 wave data is only used for PAM4 verification. The drive level into the received SerDes input is varied from small signal to larger levels, pushing the device into nonlinear compression. The following pages discuss the data collection requirements. The receive input waveform. The receive SerDes input waveform data is collected at TP4 with the received SerDes replaced with the load resistance RL for each corner case. RL is per pin and is the load resistance per pin based on the S2P data from the prior slide at 0 Hz. Note that RL per pin is related to the SDD11 characteristic of the S parameters and the Z0 characteristic of the S parameters, with the user-defined corner case channel is assumed. The receive SerDes output waveform data is collected at TP5 for each corner case. The drive level into the received SerDes input is varied from small signal level to larger levels, pushing the device into nonlinear compression. Here are waveform details. This figure represents a typical captured receive SerDes waveform at TP4 or TP5. The bit rate is the minimum bit rate, where the maximum, which is the maximum bit rate divided by the minimum bit rate, is an integer. The waveform time step is no larger than 1 divided by the maximum bit rate divided by 32. 250 to 1000 UIs of a PRBS pattern is captured. Within it, there must be a set of consecutive N0s and M1s where M and N are large enough to allow for settling of the rising and falling waveforms. This is a typical schematic used for data collection. Be sure that TP4 has the proper load resistance, which is based on the receiver circuit input S2P data at 0 Hz. Set the TX source at same as our load. The Rx SerDes input is varied from small signal level to larger levels, pushing the device into nonlinear compression. Collect the TP4 and TP5 data together into one data file for each receiver state. The waveform file details. There is one file used for each receiver SerDes AFE with nonlinearity state. The output file is a text file with these columns. Column 1 is time, column 2 is the NRZ waveform, column 3 is the receiver input into the properly terminated load resistance, and column 4 is the received SerDes output. Use a file name that includes the received SerDes name, corner case, and the names of any control parameters. If there are 32 AFE states and 5 signal levels, then there are 160 waveform files. The nonlinearity characteristic. This is a plot of a typical nonlinearity characteristic. The Vout at TP5 is collected as Vin at TP4 is varied and collected into a text file. Be sure to capture from minus saturation to plus saturation. The nonlinearity file details. Each swept DC response from TP4 to TP5 is collected with one file for each received SerDes AFE state. The text file contains these columns. The column 1 is the input DC stimulus level, and column 2 is the receive output DC response level. Use a file name that includes the received SerDes name, the corner case, and the names of any control parameters. If there are 32 AFE states, then there are 32 nonlinearity files. The receive output waveform characteristics. This plot shows a typical output waveform characteristic as the input level is varied from small signal 25 millivolts into compression 400 millivolts. Here's the slide. As the waveform level is varied, you can see that there's compression as the input level increases to 400 millivolts. again, 25 millivolts is the small signal level. Here's another view of the same data, but with the step level normalized as the input is varied from small signal to compression. With this view, you can see that as the output goes into compression, the pulse gain decreases and the pulse shape factor flattens. Processing the small signal data. The receiver small signal data collected in the prior slides is processed by the SerDesDesign.com tool, Receive SerDes Small Signal Modeling Tool. This discussion is just to give an overview of what is done by SerDesDesign.com. The IBIS S2P data is converted to an appropriate S4P file and impulse response. This S4P file is used as the IBIS buffer. The set of small signal waveform files are combined into one file. All files should use the same NRZ pattern. All file data is checked to have the same time values with monotonically increasing time. There will be 1 plus 3 times k columns in the combined file where k is equal to the number of CTLE states. This combined file contains all the original data. The waveform segment with the consecutive N0s and M1s is extracted from the combined file. The extracted receiver input waveform segment is convolved with the IBIS buffer impulse response. The modified receiver input waveform segment is de-embedded from the extracted receiver output waveform segment to form the receiver step response waveforms. The receiver step response waveforms are used in the AMI model. The receiver IBIS-AMI model is based on the IBIS 7.0 specification or higher. This block diagram summarizes the signal processing. H of S represents the receiver circuit input to the CTLE output transfer function. This is based on the receiver CTLE input output waveforms. At small signal levels, this is assumed to be LTI. H1 of S represents the IBIS portion and is derived from the S2P data. H of S is based on the circuit data, where H of S is equal to H1 of S times H2 of S, where H2 of S represents the AMI portion and is derived as discussed in the prior slides. H2 of S is equal to H of S divided by H1 of S. Processing the large signal data. The receiver large signal data collected in the prior slides is processed by the SerDesDesign.com tool, Receiver AFE NL Modeling Tool. This discussion is just to give an overview of what is done by SerDesDesign.com. The set of large signal waveform files are combined into one file. All files should use the same NRZ pattern. All file data is checked to have the same time values with monotonically increasing time. There will be 1 plus 3 times k times n columns in the combined file, where k is equal to the number of AFE states and n is the number of signal levels. This combined file contains all the original data. The waveform segment with the consecutive N0s and M1s is extracted from the combined file. The extracted receiver input waveform segment is convolved with the IBIS buffer impulse response. The modified receiver input waveform segment is de-embedded from the extracted receiver output waveform segment to form the receiver step response waveforms. These receiver step response waveforms are compared to the small signal responses, and nonlinear compensation factors are derived that will be applied to the small signal data and used in the AMI model. The IBIS-AMI model is based on the IBIS 7.0 specification or higher. This block diagram summarizes the large signal processing. The filter is the H2 of S from the small signal data. The filter is raised to the root power, where R is equal to root value, with a gain called gain factor. The root value is equal to 1 at small signal levels. Root value is less than 1 at larger signal values. The nonlinearity causes the filtering to flatten out as the input level increases into compression levels. G is the gain split and is a factor before the nonlinearity with the 1 over G applied after the nonlinearity. Root value, gain factor, and gain split are derived for each AFE state at each derived level. Converting the process data into an IBIS-AMI model. The receiver IBIS-AMI model for discussion in this report per the IBIS specification is a nonlinear and or time variant model, NLTV. It has an IBIS file that includes a model section with model type equal input. It has an IBIS circuit defined that is ignored because the one defined by the S4P file is used instead. The AMI file has reserved parameters that define the IBIS portion as the S4P file. So in the AMI file, there's the parameter TS file that defines the S4P file, and there's the parameter RxR that defines the load resistance, which will be set to infinite impedance using 1 e to the 9. Using the IBIS-AMI model building project. An IBIS-AMI model building project is included in this receiver AFE nonlinear modeling tool. Use of this tool is only dependent on the installation and use of the free Microsoft Visual Studio tool. See the instructions included with the tool. Use the getfiles.bat script to copy the CSV and S4P files generated from the prior steps. This project contains these files and folders. The files from the small signal data and from the large signal data I highlighted. The other files are for the IBIS-AMI models. Generating the IBIS-AMI model. When the Visual Studio tool, when Visual Studio is run on this project, then the required IBIS-AMI models are generated and installed into the release folder. These files can be used in any channel simulator on the Windows PC. Use of the modeling tool allows you to create any number of receiver AFE nonlinear IBIS-AMI models with the same licensing limits as the tool. Validating the receive IBIS-AMI model. The generated receiver IBIS-AMI model will be tested against the original receiver waveform data that was collected into the one combined file. For small signal data, the validation will show excellent agreement between the receiver IBIS-AMI model output and the original receiver Rx waveforms. For large signal data, the validation will show excellent agreement between the receive IBIS-AMI model output and the original receive waveform for peak and step levels. The waveform shape will have excellent agreement towards the small signal level, and the waveform shape will have some deviation as the large signal increases. Here are typical validation waveforms. For the data displayed earlier, the model has excellent agreement with data for all AFE states and levels. Here's a display for 4 input peak-to-peak levels. The reference original data is in red. The model output is in blue. As the input signal level increases, the output response flattens and spreads out and the gain compresses. Still, the model and data have excellent agreement. Summary. This webinar has shown you how to achieve a perfect receiver AFE with nonlinearity IBIS-AMI models for SerDes channels based on circuit data, where at small signal levels, perfect means that the IBIS-AMI model output waveform exactly agrees with the circuit output waveform. At large signal levels, perfect means that the IBIS-AMI model output agrees with the circuit output for peak and step levels with some variation in the pulse shape allowed as the signal goes into compression. In this webinar, you learned how to convert the S2P data into an S4P file and its equivalent impulse response. You learned how to generate waveform and nonlinearity data files from circuit simulation. You learned how to extract the desired waveform segments with N0s and M1s, and embed the input waveforms plus S4P impulse from the output waveforms. Also, you learned that the Rx NLTV IBIS-AMI model is generated from the circuit data. These steps are automated with the tool SerDes IBIS-AMI Rx AFE with NL modeling tool. Here's some further considerations. SerDesDesign.com has many other tools available. They're available at the store listed at the SerDesDesign.com home store webpage. There's a channel simulator for a single channel system, same as used on the free web-based tool, and uses your PC processor and your file directories. There's a IBIS-AMI model generation tool, convert any included transmit or receive behavioral model into IBIS-AMI models. It includes the SerDesDesign.com Windows and Linux IBIS-AMI model development environment. There are additional tools available for transmit FFE modeling and for receiver CTLE modeling. So, with this webinar, I'm introducing you to your personal Windows PC copy of my SerDes IBIS-AMI Rx AFE with Nonlinearity Modeling tool. It's based on processes I've used successfully with my customers over many years. It automates the use of circuit simulation data in one step. It includes IBIS-AMI model building environment and automates the creation of an unlimited number of receive AFE with Nonlinearity IBIS-AMI models. Here's what you get. You get the ability to automatically convert S2P data to IBIS S4P models, automatically combine circuit simulation waveform data, automatically extract the desired waveform segment, automatically de-embed the input waveform from the output waveform, automatically generate the receiver IBIS-AMI model, and you can generate any unlimited number of receiver IBIS-AMI models. Includes instructions and examples. So check it out on my dime. I personally guarantee that you'll be successful using the Windows PC copy of my SerDesDesign.com tools. You have a full 30 days to put it to the test. After that time, if you see the value in it, then you can buy it. I only want you as a customer if you're 100% happy with your investment. Simple as that. Each of my SerDesDesign.com premium tools comes with a node-locked time-based license. Use of the tool is free for 1 month. After you're happy with it, then you can decide to purchase a 12-month license. See ordering instructions for your free copy of available tools at this website for SerDesDesign Premium Tool.pdf. See the link below this webinar presentation as well. This ends my presentation content for this webinar. I'll end the recording of the webinar and spend time with you to address your comments and questions. Remember, you can also email me with your comments and questions at johnb@serdesdesign.com. Thank you.